This video goes over motion in 2 dimensions or 3 dimensions, i.e. multiple dimensions. The definitions are identical to the ones that you learned in 1-dimensional motion. However, with multiple dimensions, there is additional complexity. If you're already familiar with the definitions within kinematics and want to go straight to the maple, go to about the 5-minute mark. Otherwise, let's get started. All right, we begin by looking at the definition of position in 2 dimensions and 3 dimensions. In 2 dimensions, positive x will always point to the right, negative x will point to the left. Positive y will always point up, negative y will always point down. Therefore, in 2 dimensions, any point is a combination of its x component and y component, and that's what we mean by the position r as a vector. In 3 dimensions, x and positive y are the same, and positive z is coming directly out of the whiteboard, out of the computer, out of your page. I'm trying to show this in 2D, but that's the idea. Again, any position is now a component of its x component, y component, and z component. Since this is a video about physics and not vectors, go see the vectors video to see how to calculate the magnitude of our vectors. I've included 3 particular examples: the square root function that you can make, the vector calculus double absolute value sign technique, or the linear algebra norm. In calculating this angle from the positive x-axis counterclockwise up to the vector, in 2 dimensions, you use the arctangent function. Again, look at the vectors video for more examples. Regardless, remember that position, which I define as r, and is based on its components of x, y, and z, are all functions of time. Therefore, each component is a function of time. Next, we define velocity, which is going to vary with time as well. We can plot velocity as a vector by saying there's an x component and a y component to it, and this is the direction in which the object is traveling. Velocity is defined as the time rate of change of position. You can either do in 2 dimensions or in 3 dimensions. Since velocity is going to be defined by most of my problems in terms of component, and since each component is a function of time, therefore velocity as a vector is a component of time, and therefore in a sense, by defining the way we did of what velocity is, each component is defined as well. I'll just mention at this point also that we can define speed, which is not a vector, but it does vary with time, as the magnitude of the velocity, which varies with time. If you understand that if we have an object with mass, and this represents its velocity vector, i.e. the direction it is traveling, either in 2 dimensions or in 3 dimensions, if we weight this velocity vector with the fact it possesses mass, we are talking about momentum. Momentum is a key component in dynamics. That's why I introduce it now. Its definition is, again, mass times velocity divided by this factor. This factor generally is very close to 1 if v is small compared to c, the speed of light. And of course, if it's small and you square it, it's even smaller. So normally this factor is close to 1. But if objects are moving greater than 1/10 the speed of light, you have to include this factor. Most objects are moving far less than 1/10 the speed of light. So to very, very good approximation, momentum is just mass of the object times its velocity. The last definition is acceleration. Acceleration is the time rate of change of velocity. It is a vector because each component of the velocity vector gets differentiated with respect to time. Getting a feel for acceleration can be challenging and is best done in an experimental environment. So putting these ideas together, the modern approach to thinking about position and how it changes is due to the fact that momentum exists. And thinking about how momentum changes is due to the fact that there is a net force on the object. In most textbooks, we approach the idea that position changes because of velocity, and velocity changes because of acceleration. Dynamically, this is incorrect because interactions, i.e. forces, are what causing things to change their position, momentum, or velocity. Let's get to how Maple can be used with these definitions. So I'm going to find the equation of the velocity vector, which varies with time, as the time rate of change in position. And I'm going to define the acceleration definition equation as acceleration is the time rate of change of velocity. Next, each vector is made up of its components. And so in Maple, you have to list out those components, x, y, z, or vx, vy, vz, etc. Again, all these are functions of time. Our goal here is to use these definitions of acceleration and velocity to determine the position due to the fact we may know acceleration. To do this, we have to include some initial conditions. Here are two initial conditions that we have to provide. For example, the initial velocity at some initial time is going to be some value. The initial position at some initial time is some other value. And as before, since we have to define our vectors in terms of components, we do the same things with these initial values. Given this information, we can solve for our definitions, provide our initial conditions as a set of equations, and we define that the components of V are related to A. These are dummy variables Z1 for both Vx, Vy, and Vz. And positions are double integrals involving A and the initial position. Given the fact that V and A are defined by derivatives, it's not surprising that R, each component of x, y, and z, and V, Vx, Vy, and z, are defined in terms of integrals. So with our solutions here, what if we defined our acceleration components as constants? What is our solutions now? This looks pretty complicated. Let's define the initial time we start at 0. Evaluate our solutions at t sub 0 equals 0. You get the sort of classic equations you probably have to memorize. One for x, y, and z, and also for position x, y, and z. I'm going to make functions out of the solutions of x and y in only 2 dimensions. Define these acceleration components as the same and create an array of plots in single quotes so they don't get executed until when I need them to be executed of position and velocity, and explore these plots for the varying constants that we can put in for x, y, and for v sub 0 and v sub x and our acceleration. And this is the plot we get, assuming we start at x equals 0, y equals 0 with no initial condition, and all we're doing is accelerating in both the x direction and y direction. As we vary x, you can see how the xy plot changes its initial position. If we vary y, you can see how it varies in the vertical direction. If we change the value of v0x, you can see how it changes in the velocity direction and has an impact in the position. So it's traveling like that. And you can do the same thing for y. And again, you can vary the acceleration depending upon whether you're going up to forwards or backwards. Returning to our solutions, which were solutions involving time, what if we have an acceleration that depends upon velocity? Here's one where the a sub x depends upon v sub x and a sub y depends upon v sub y. Can we still use these solutions? And the answer is no. We're still stuck with a situation where we're trying to solve for velocity in terms of integrating itself. As a consequence, these solutions only work if acceleration is a function of time. If we're working with more realistic problems, we have to return to our initial setup, redefine it before we execute desolve. So let's return to the definition equations, which I've written out one comma the other, and I've defined each of my vectors in terms of their components. And since we have to provide some initial conditions for this situation, I can define position as 0, where 0 is really a vector of 3 zeros and some initial velocity. We can now solve these definition equations and include the initial condition equations and find out what v of x, v of y, and v of z, and x, y, and z are as functions of time. And as before, we'll define our functions, and of course we have to be more specific now. This is what acceleration is in terms of its x component and y component in terms of v. We will make an array plot of both position, velocity, and time, integrating from 0 to big T, and explore. Again, depending upon what our initial velocities are, we will affect how the motion of the object is, will affect how its velocity changes with time, and like that, and again with the acceleration as well. So initial conditions and whatever the accelerations are values have an impact on position, velocity, and acceleration. We finish with an example that requires a numerical approach. Same definitions for velocity and acceleration, same components for r and v, but now we're going to say acceleration is a magnitude of r squared times r and a magnitude of v times v. And while we need to still provide initial conditions, it is clear, given the definition of acceleration, this problem cannot be solved numerically. Therefore, all the constants and all the initial conditions must be defined numerically. So we now use dsolve again for our equations and our initial conditions, but now we're going to solve it numerically, and I will make the output a series of procedures. Extracting the solutions, and this time I'll do it in 3 dimensions. You may note, though, I did not make vectors out of these. I actually made them a list in terms so that we could use a plotting package. And now we're going to make an array of space curves for both position and velocity because I want to plot them versus as a function of time. And they look something like this. So here is position. As it travels from here around, comes back. This is our velocity, starts with an initial position, goes like that again. And we can animate this as a 3D plot of its position, like as a point, representing the point as a solid sphere, so that when we click on it, it moves around in its pattern. Kinematics, the motion of an object with mass, such as a particle, is essentially 2 definitions, that of velocity and that of acceleration. The complexity of this segment is it includes not just one dimension, but multiple dimensions. Therefore, the math is a little bit more complex. But the physics is identical as long as you keep it in a component format, which is the easiest way to do these types of problems. The next video will be on example problems in multi-dimension kinematics. As always, leave questions, and if you want, look at the attached document.